so we're going to talk about waves and simple harmonic. Okay, so we're going to talk about waves and simple harmonic motion. So, you know a little bit about waves. You've thought about waves in the ocean. You probably have heard before that sound travels in waves, okay, and so does light. We're going to get into all of those things. So today we're just going to kind of talk about a wave in general. So when we draw a wave, it looks like this, okay? And this part right here is called the amplitude. The amplitude is the maximum displacement, so we're going to the highest point or the lowest point. We could go down here and measure it, from equilibrium. And this is our equilibrium position, okay? Then we have crests and troughs. So basically your amplitude goes from your equilibrium to the top of your crest, or you can go to the bottom of the trough and just take your absolute value. Okay, you want to find the amplitude. So again, crest is the highest point, trough is the lowest point from the equilibrium position. Wavelength is the distance between two adjacent from math, means next to each other, similar points of the wave, okay? So from here to here, those are two crests, okay, that are next to each other, so we get our wavelength, okay? I cannot measure from here to here. Students like to do that a lot. They're both equilibrium, but it's going down here and up here. I would have to go from equilibrium up to equilibrium up, or equilibrium down to equilibrium down. Lots of times it's nice just to go from crest to crest or trough to trough, okay? Makes it somewhat easier. So there's two different types of waves. The first is a transverse wave. This is a wave whose particles vibrate perpendicular to the direction of the motion, okay? So they're going, the wave is traveling this way. Think of it kind of like a ocean wave. It's going in towards the shore here, or the shore over on this side, okay? But the particles are actually going up and down, okay? And if you watched in the ocean, sometimes you can ride a little bit of the wave in, but a lot of times you're just out there and you're just bobbing up and down. You're not actually going to go in, okay? And these particles just kind of go up and down in the same spot. So it's a wave whose particles vibrate perpendicular to the direction of the wave's motion as the wave goes that way. A longitudinal wave is a wave whose particles vibrate parallel to the direction of wave motion. So I'm going to think of this as kind of looks like one as well. It looks like a slinky or a spring, okay? So you kind of bunch it up back here and then let go, and you're going to watch that bunch just kind of travel throughout, okay? And all of these actual parts of the spring, this actual part of the spring isn't going that way, but the group, they keep getting grouped closer together as they travel, okay? So the wave is traveling this way, okay? And these little parts of the spring are just going to vibrate back and forth parallel to that direction. So again, a wavelength, this is kind of like you're going from compression to compression, okay? And then where they're spread out as well, the refraction. All right. So now, when we're talking about waves, the first thing we're really going to do is look at simple harmonic motion. We're going to do so with a lab. So simple harmonic motion is a vibration about an equilibrium position in which a restoring force is proportional to the displacement from equilibrium. So if you're thinking about a pendulum, which we've got a picture of a pendulum up here on this clock. Okay, I'm going to make this pendulum swing farther than it could. But if I pull the pendulum all the way over here, okay, the restoring force, when I pull it over here, is going to be more. That means the force it takes to get back. So it's going to be like the force it takes to return to here is going to be more so than if I only pulled it this far, okay? You could also think of it as a spring, okay? So if I stretch the spring just over, so we're going to say we're starting here, okay? I'll leave that one where it is. I'm going to stretch it to here now, okay? The restoring force is going to be a little bit less than if I stretched it all the way down to here, okay? Because the restoring force is proportional to the displacement from equilibrium. This is my equilibrium, it's not moving here. And this is equilibrium because it's, it's not going to go anywhere if I leave it there, all right? So examples, pendulum mass on a spring, we are going to look at both of those in some labs. Then we've got period. The period is the time it takes to execute one cycle. It's measured in seconds. So one cycle would be, if I started all the way over here, it would be the time it takes to swing over and back. So that's one cycle, so however long it takes to go from here and back, okay? Or if I'm looking at this spring, maybe I stretch it all the way down to here. It would be the time it takes to go back this way and then all the way back down. That would be the period. So it's the time it takes to do one cycle. It's measured in seconds. And the symbol is the capital letter T because it's measured in seconds. It's a time. It's the time for one cycle. Then we've got frequency. Frequency is the number of cycles or vibrations per unit time. So it's how many times does it go back and forth in a second. Now these one up here, it's going to be more. It's not going to be very many. It'll be like part of one. But maybe that spring is vibrating really fast. It's going back and forth like 10 times in a second. Okay, that would be its frequency. It went back and forth 10 times in a second. It's measured in hertz. A hertz is 1 over a second. Okay, so the frequency is how many times it's going to vibrate per second. There is a relationship between frequency. Also, frequency is given with we've got our symbol of the lowercase f. Frequency is equal to 1 over the period. Okay, so you can solve for frequency that way. All right.